I wanted to talk a little bit more about the spring force and specifically show you that it usually results in a non-constant acceleration. Our acceleration will be a function of position. What I have drawn here is just some horizontal surface on which a mass rests, and we're going to say it's frictionless. And I went ahead and drew an equilibrium line. An equilibrium line is where the spring would be if it was neither stretched nor compressed. Well, we're going to stretch it a little bit. That was horrible. We're going to stretch it a little bit. Some delta x. Alright, and let's do a free body diagram. If I represent this as a point mass, I can go ahead and draw mg down and the normal force up, but it's not going to give us any information because this is frictionless. Since we pulled the mass and the spring to the left, we are stretching it. It wants to go back this way, so we have a force due to the spring acting to the right. Now, if I do Newton's second law, the summation of the forces in the x direction is equal to the mass times the acceleration. I just have that spring force. I just have the spring force is equal to mass times acceleration. The spring force, we have a definition for it as the constant times the displacement. Go ahead and substitute that in here. And that equals the mass times the acceleration. Alright, right here, if I solved it for acceleration, I get k over m times delta x. Meaning, if here's our equilibrium position, here's where the spring was attached to, at every different delta x, we're going to have a different value for acceleration. So this is not constant. You would have to use something like acceleration is equal to dv dt, rearrange and integrate, or it's a function of position. More likely you could use v dv is equal to a ds and figure out a new kinematic equation for this particular acceleration. That's still a little at the advanced level. You need to be aware of it. I could still say, okay, well, if k was equal to 10 newtons per meter and the mass equaled 1 kilogram and we stretched it 0.5 meters, we can still get a value for the acceleration, right? But we cannot use that value to figure out its velocity 2 meters later. We would have to come up with our own kinematic equation from this. So you can't use constant acceleration equations. Type of problems that we will be solving though is what if we'll have spring forces added in, and they just add just like any other force. But imagine, let's just do something real quick. What if they said we have a mass hanging from a ceiling from a spring, and they say it is hanging some delta y is equal to 1 meter. Let's say 2 meters. I'm going to use some easy numbers. Some 2 meters. But they say its unstretched length is equal to 1 meter. Well, that means it's stretched 1 meter. Alright? From that we could figure out the spring force. They could, what if they didn't tell us how much it was stretched? What if they said the spring constant is equal to, let's say, 5 newtons per meter? Let's say the mass is equal to 1 kilogram. And let's figure out, let's say if this is in static equilibrium, meaning it's not moving, right? Its acceleration is 0. How much is the spring stretched? Okay. Here's our mass. Let's go ahead and do a free body diagram. I have a mass with mg pointing down, and if we displaced it some delta x, if you had a mass hanging from a spring, the mass is going to cause the displacement to be in the downward direction, right? That's how things work. Because the only force acting on it, it would have to be pointing downwards, and that means the spring force would be pointing upwards. Now we could say the summation of the forces is equal to the mass times the acceleration in the y direction. We just have a spring force and mg. And we can say if it's in static equilibrium, that goes to 0, so that the spring force is equal to mass times gravity. Now, how much is the spring stretched? Well, we could say our definition for the spring force is it often has a minus sign in front of it. I recommend getting your sign directly from your free body diagram. So in this case, I have a positive k delta x equals mg. Now we know m, we know g. I gave the spring constant k, that's in newtons per meter. And we can figure out delta x, or the spring stretch. In this case, it would be mg over k. The mass was 1 kilogram. The acceleration due to gravity is 9.81 meters per second squared. And k was given as 5 newtons per meter. Alright, so there we can calculate delta x. That's how much it is stretched if it was in equilibrium. Doesn't have to be in equilibrium, but for now, most of the spring problems will be on the more fundamental side, because we will be able to solve more complicated problems and do it more easily and figure out more information once we actually use energy methods in our next unit. So hang in there, but don't forget anything we've learned.